Hey guys, Mr. Brown here. The following presentation is about the properties and nature of light. Light, contrary to most of the focused topics in chemistry, is a form of energy, not matter. We care about light in chemistry because most of our understanding about the properties and behavior of matter are based on its interaction with light. In this video, we are going to learn how science describes light, talk about a few of the important experiments that help develop our understanding of light, and how its characteristics are defined and measured. One of the first scientists to systematically evaluate and describe light and its properties is none other than the great Isaac Newton. Newton, famous for his theory of gravity and for the development of calculus, also spent some time developing optics that could bend and diffract light. He was one of the first to show that white light could be separated out into different colors and then recombined back into white light. Newton explained the behaviors of light using a corpuscular theory, in which he said light was made of tiny particles that had different properties like speed, which is where the different colors came from. Newton was on one side of an argument, however, as many other scientists felt like light could better be described as a wave. Around the turn of the 19th century, a scientist by the name of Thomas Young settled the debate about the nature of light with what is now known as the double-slit experiment. By carefully crafting an apparatus that allowed light to pass through two meticulously spaced slits, he was able to demonstrate that light exhibits interference patterns, much like those observed when two waves on the surface of a body of water meet. In some areas, the waves constructively interfere and get larger, a higher wave in the case of water and brighter spots in the case of light, while in other areas, the waves destructively interfere. In the water wave, they are flattened out. In the case of light, we see dark spots from this destructive interference. Later, in the 19th century, James Clerk Maxwell publishes his theory of classical electromagnetism. This theory describes the nature and behavior of electric charges, magnetism, and the fields they produced. He correctly predicted that light is a form of energy formed in these fields that radiates as waves when electric and magnetic forces move. These waves are now called electromagnetic waves. You can see an animation of electromagnetic waves here, where they are shown as propagating perpendicular electric and magnetic fields moving through space. Electromagnetic waves, like all waves, can be defined by certain characteristics. All waves are periodic oscillations that transport energy from one place to another without transporting matter along with that energy. Mechanical waves do require matter to travel through. Electromagnetic waves do not. They can propagate through empty space. All waves, no matter the origin, have the characteristics wavelength, frequency, amplitude, and speed. You can see a diagram here that illustrates the first three. Wavelength describes how long a wave is, amplitude describes how tall a wave is, and frequency tells how many waves are passing through a given point per second. The fourth characteristic, speed, is a function of wavelength and frequency. It describes how much wave travel is taking place every second. Mechanical waves can vary greatly in their speed. Ocean waves near the beach typically have a speed of about 10 kilometers per hour, while the speed of sound in air is about 1,200 kilometers per hour. Electromagnetic waves have an enormous speed that is always constant in the vacuum of space. It is 2.998 times 10 to the 8 meters per second. This is known as the speed of light. Here on this slide, I have an animation that I have always found interesting. It shows the speed of light on a planetary scale. The first image shows how long it takes for light to travel around the Earth, while the second shows the amount of time it would take for light to travel to the moon. So for instance, if you were to turn on a flashlight and point it at the moon, it would take that long for the light to travel from your flashlight and reach the moon. The next two images show the scale from here to Mars and from the sun to Earth as well. I wonder if you expect this to be slower or faster. Electromagnetic waves, because of their constant speed, display an inverse relationship between the wavelength and the frequency. If one gets larger, the other, by necessity, must get smaller. This relationship can be expressed by the formula c equals lambda times nu, where c is the speed of light, lambda is the wavelength, and nu is the frequency. When calculating problems using this formula, always be careful to make sure wavelength is given in or converted to meters, as it is often conventional to give this measurement in nanometers. Practice examples for problems with this formula can be found on the examples video. So now we are around the year 1900, and it is accepted that light is a wave, part of this continuous spectrum of radiative energy known as the electromagnetic spectrum. Today we rely on electromagnetic energy for many things, not just vision. Some of the invisible, longer wavelength electromagnetic radiation is used to transmit information. This is what is used to transfer the data in radios, TVs, phones, Wi-Fi, and other tech devices. Some of these waves, known as microwaves, are used to heat our lunch, while infrared radiation is used to see in the dark and to control our TV from the couch. Some of the smaller wavelength radiation is used for medical imaging and when producing nuclear power. One small fraction of these types of electromagnetic waves indicate a response in the cells in our eyes known as cones and rods. Thereafter, a signal is sent to our brain. This specific type of electromagnetic radiation is what we call visible light, and it is only a tiny fraction of the entire spread of electromagnetic radiation. Like mentioned previously, this work was all taking place around the turn of the 20th century. The advances in understanding were so great that many scientists thought that physics was complete. Maxwell's equations had accurately described the behavior of electromagnetism, while the mechanics began by Newton accurately described the behavior of matter. Pioneers like the guy pictured here, Thomas Edison, took this knowledge and started to engineer history-changing technology like the electric light and the telegraph. There were a few lingering inconsistencies, but most scientists thought that these would eventually be corrected by ever-improving technology. What they didn't know was an entirely new branch of physics was just on the horizon. One of the lingering problems with classical electromagnetism was its inability to correctly model the behavior of blackbody radiation. Blackbody radiation is the light that is produced when something is heated. Think about the eye of an electric stove. As it gets hot, it starts to turn orange and then get brighter and brighter until it is very hot and much whiter than when it started. The models related to Maxwell's equations, which were so good at predicting so many other behaviors, were incorrect about this particular phenomenon. In fact, above 5,000 Kelvin, the classical models predicted that there would be an infinite amount of ultraviolet radiation produced. If this were to be the case, you would be hit with the energy of a supernova every time you open the door to your oven to check on the bread. Obviously, this is not the case, so that meant there was something wrong with the model. The solution to the problem was provided by a scientist called Max Planck, who had to propose something so odd that even he did not like having to do so. He was able to fit his model to the observation by restricting the energy of vibrating atoms to certain values in particular, known as the quantization of energy. He was basically saying that energy has a packet amount that it's allowed to come in, where the classical model had no such limitations. This is like saying your car is only allowed to have certain speeds. For instance, you pull out of your driveway and you're only allowed to go either 0 or 5 or 10 or 15 miles per hour, and nothing in between. Although Planck himself did not care for the solution, there was no denying his model fit the observation much more closely. Another lingering question was that of the photoelectric effect. It had been observed that when light was beamed at the surface of a bare metal, electrons were ejected. According to classical wave theory, the energy of a wave is related to its amplitude, which is correlated with the brightness of light. So a brighter light should eject electrons with more energy. Furthermore, classical theory predicted that light of any wavelength should be able to dislodge an electron given enough a time to absorb the energy. However, again, classical electromagnetic models did not fit observation. In reality, it was observed that electrons were ejected only when light of a given frequency was shown on the metal, and that increasing the frequency increased the energy of the ejected electrons. Additionally, increasing the brightness of the light only increased the number of electrons ejected, not their energy. These observations were explained by Albert Einstein himself. Basing his explanation on Planck's idea of energy quanta, Einstein posited that light was composed of a stream of particles, now called photons, that have an energy related to their frequency. His explanation detailed that only photons with high enough frequency could dislodge an electron from the metal surface, and that higher frequencies ejected electrons with more energy. The intensity or brightness of the light related to the number of photons present, which is why higher intensity light ejected more electrons. This explanation was the first view of what is now called the wave-particle duality of light, in which it is recognized that some properties of light are best described as a wave, and some properties of light are best described as a particle. Einstein gave an equation for the energy of a photon found here. You can find practice with this formula on another presentation. I'd like to note that it is this work for which Einstein won a Nobel Prize, not for his more famous theory of special relativity.